Okay, once again, thank you very much for joining the October version of the Liftoff webinar series featuring PDA LLC. We can learn a little bit more about them in just a second when they get started. I have a few housekeeping issues to take care of before we get the presentation rolling. The first is to please put your phones on mute. The less background noise we have, the better for the presentation, and everyone will be able to hear and understand what is going on. Secondly, if you have questions, please use the chat function on the GoToMeeting taskbar that you see. It's on the right-hand side of my screen. You can address the question to the organizer. That question will come to me, and we can facilitate the Q&A at the end of the presentation. Finally, each Liftoff webinar is recorded, so we are recording this one today and is posted on the Lift website for future viewing. So if you want to miss something and you want to go back and check it out, or if you want to share it with friends and family who are unable to make it today, I would certainly encourage you to do so. If you want to get in contact with this organizer or this presenter or any of the other presenters in the past, please go ahead and take a look at those presentations and reach out to them with any questions. A little bit about Lift. We are, for those that don't know, we are a proud member of Manufacturing USA. It is a network of 14 innovation institutes that are around the country, each focusing on a unique R&D technology. The whole goal of Manufacturing USA is to reinvigorate manufacturing in this country, both from an R&D point of view as well as an education workforce point of view. So the technology that we focus on is lightweight metals. We have a mission to accelerate the development of and application of innovative lightweight metal production and manufacturing technologies to benefit both the U.S. commercial and defense markets. So we really do that in three different ways, actually. The first is the R&D that I mentioned. You can learn about our R&D projects by visiting us at lift.technology. We have a wide portfolio of technology projects underway, mostly in the transportation space, everywhere from shipbuilding to aerospace to automotive, and certainly just announced today the completion of a project that we did with a very small company with innovation they developed to help firefighters, actually. So you can take a look at that at lift.technology. We also, the next step is technology transition, which is helping to take that new technology and get it rolling into the marketplace. There's no, doesn't benefit anybody to develop a new innovation, new technology, just leave it sitting on a shelf. So we work with companies to do just that and transition it into the market. Finally, we want to make sure that there are people with the knowledge, skills, and abilities to work with these new innovations and new technologies in the industry, on the shop floors and elsewhere. So we have a wide array of education workforce development programs that we've invested in. We are investing in our facility here in Detroit, the Lift Learning Lab, which we will be opening up next year to as an expansion of the education workforce development initiative. So we will have hands-on capabilities to open folks' eyes to manufacturing and engineering going forward, as well as teaching incumbent workers, upskilling, things like that. So stay tuned for more to come on that. Finally, about our facility, I mentioned the facility here in Detroit. We have a number of large pieces of equipment that are open for R&D. We share space with another of the Manufacturing USA Institutes, ICME, which focuses on composite materials while we focus on lightweight metals. You can see a list of some of our pieces of machinery on your screen. We actually just took ownership of the linear friction welding machine, the only one in the country available for R&D. We just took possession of that within the last 2 weeks. So it is currently being installed, and we look forward to that coming online and available for R&D work as well. So please reach out to us for any of the machines you see online on your screen, or any of our network partners actually as well. We have a wide network of industry and academic partners, so we can team up with all of them to serve your lightweighting innovation needs. you can reach out to us at lift.technology, or communications@lift.technology is the email address as well. The Liftoff webinar series is brought to you by both LIFT and the Michigan Manufacturing Technology Center. I don't know if we have anyone from the center on the phone. Let me ask real quick if anyone from the center is on the phone. All right, hearing none, we will just plug along. The center is part of the MEP, the Manufacturing Extension Partnership, which is funded also federally through the National Institutes of Science, Standards and Technology, NIST, out in Maryland. And each state, I think there are 51 MEPs around the country. The Michigan Manufacturing Technology Center, as its name would imply, is Michigan's. And their focus is helping small and medium-sized manufacturers, not just manufacturing metals or composites, but manufacturing any number of things, from including food, for example. So you can see some of the services they provide there. They've been a longtime partner of LIFT, and we are proud to have them as a partner and as a co-presenter of this webinar series. So please, if you have questions about cybersecurity or accelerating your technology, or doing some research for you, please reach out to the center. You can see their website on the screen. They are located over in Plymouth, Michigan. So I'd encourage you to do just that. Now, enough about LIFT and the center. I want to turn it over to Jiten Shah from PDA LLC to provide today's presentation on lightweight casting. So I'm going to give him the presentation and the floor. Jiten?
Great, Joe. Good morning, good afternoon, wherever you folks are. I'm Jiten Shah, founder and president of Product Development and Analysis LLC. Joe, you can hear me okay?
Yes, I can.
Excellent. So we are going to share some of the work we have been doing in partnership with LIFT, along with a few of our projects internally, and talk about the process. So my content, quick introduction, the lightweighting process, the technologies, a few concerns for making successfully thin wall castings that we learned and we researched through the LIFT project that we'll be sharing. And I'll wrap up with some case studies. So we are, this is our 25th year. We actually started the company offering engineering services to metal caster OEMs and the foundries and the tool makers. We have served over 150 OEMs and casters and tool makers. We are a member of 3 institutes, including LIFT. Worked on 3 projects on thin wall castings. Also a gold member of America Mix, which is focused on 3D printing or additive manufacturing. And also a member and had projects working on Digital Manufacturing and Design Innovation Institute out of Chicago. And we do support the military DoD folks as a subject matter expert on casting and composite. You can see the membership. So what we do is our mission is to understand customers' requirements and concerns, come up with a solution which fits in their needs on cost and time. And most of our projects we are heavily on solution, virtual simulation driven solutions, including the new technologies. 25 years ago, we used to call it rapid prototyping. To me, it is another version, additive manufacturing and such. And we have really gone after our competition, which is forging fabrications and to some extent plastics. And with our help, we have added over 3,000 tons of castings in various alloys by conversion. So quite a bit of experience on that. This is in addition to the commercial work, we also get into the R&D. And this is one example working with LIPT that I'll be sharing. These are some of the tools, standard CAE, CAD, FEA, CFD, process simulation, quite heavy on that for various processes, and we have a very vast database, and 3D scanning. So I'll just jump in, with the process we use, which self-explanatory, but I would say the key is to get into thinking about the manufacturing process right at the conceptual stage. So we call it concurrent product and process development, and pay attention to customer requirements, also come up with a solution which is going to be cost effective. So look for alternatives which are economical to the client, and heavily on web collaboration and project management. These are some of the tools we use. We have internally developed casting alloy process selector, capturing the best practices that we use for selecting a process and an alloy. And CADS is another tool that we use, where we have worked with American Foundry Society to generate a placeholder for material database suited to various casting processes and alloys. And we use quite effectively the additive manufacturing as a tool to lightweighting, come up with lightweighting solutions that I'll be talking about. So the key element for a successful lightweighting project, design optimization, the value engineering, and I would say this is very critical. Evaluate the process capabilities with regards to dimensional and surface finish aspects, especially when you are going up to thin wall casting manufacturing in a production successfully. Then we get into detail engineering, all the performance validations. We do invariably go with the functional prototyping, validate, refine our model design, and then get into the production. So, it's all driven digitally from concept to finished products. And we heavily focus on optimization for the product performance, and also, as I said, manufacturing cost reduction. So, inputs, requirements, outputs could be the data package or a physical component. And we effectively use failure mode effect analysis at the design as well as at the process levels. So what are the opportunities we have for lightweighting? Obviously, if you have the time and resources, the best benefit you would get right when you are developing a new product as opposed to developing traditionally and then converting, especially with the technologies such as additive manufacturing. It offers tremendous design freedom, and you can do a lot of part consolidation, and obviously the knowledge and experience is key, even though there are quite a few new tools out in the marketplace for generating. Those are quite effective, but I would say you have to top it off with the knowledge and experience about the process and the alloy. So the new product is quite intuitive, but also redesign and reverse engineering, especially for the legacy parts, for optimization. That's a greater opportunity in my mind, where you have a legacy part and you can redesign to get the weight out and improve the performance and come up with a solution which overall is going to lead to the lightweighting of a device or an equipment or a platform. And extensively use ICME approach, and there are quite a few new alloys being developed. I'll share the one we ended up working on as part of the LIP project, and that's another way you can optimize and by redesigning the current product. So ICME is a basically integrated computational materials engineering. It's basically a way to capture the material information along with the process and simulate the process conditions, for example, cooling rate and the chemistry, and come up with predictive microstructure and properties, and ultimately plug those to validate your final product performance from the structural point of view. And LIT has a very powerful ICME task, which we belong to and contribute towards that mission. So this is very effective tool that you almost have to use in order to get any form of lightweighting or design optimization, and by using the local properties that you will expect, as opposed to using the handbook data. So jumping a little bit here, obviously for us on the metal casting, the lightweighting comes by reorganizing the features and, more importantly, thinning the walls. And how do we do that successfully in production? So these are some of the key factors that influence successfully implementing or making thin wall castings. The fluidity of the alloy, which drives how thin you can make, which is driven by the thermophysical properties, namely the viscosity and the surface tension, and the process conditions, the core temperature, which typically, with most of the alloys, the higher the temperature above the liquidus, you tend to get better fluidity. But there are, penalties with that, which I'll also deep dive. And then solidification, microstructure evolution, which is with a thinner wall, you have higher cooling rate. For directional solidified alloys, you have shorter feeding distances, so that poses a challenge with regards to feeding the casting to the soundness you're looking for. And discontinuities, especially micro shrinkage, centerline shrink, trapping the gas, and hot tear or cold cracks, especially when you go with a thin wall to very thick transitions. And it does have a restricted pathway, so tendency to capture or trap the oxides and inclusions, which are strictly driven by the alloy and how you have designed your gating system. So if you use a conventional gating and come up with a thin wall design, that may not work. You may have to redesign your whole approach to get certain critical velocities in the critical areas to get oxides and inclusions out of the casting into the risers and maybe non-critical areas. And then there is concern with the warpage and distortion, which happens while it's solidifying, and also after it has solidified during handling and subsequent processing. And then the precision of the tool contributes quite a bit to the success of the thin wall casting. especially your print clearances between the core print and on the pattern and in the core. And then normal wear and tear do add to changing those clearances and then ultimately affecting your final wall thicknesses. So how do we mitigate or come up with these obstacles and make successfully thin wall castings? Obviously new alloys which have better fluidity, rigorous simulation, ICME tools used, novel risering, gating, filtration, and venting scheme that you would need with thin wall. I would say automation in handling. This actually is our experience on one of the lift melt project where we did make thin wall castings, but we got only 30–40% at the end of the line. A lot got broken in the tumbling and shakeout operation. So it is a challenge, and you just have to think through and come up with a way of handling thin wall components. And then to completely mitigate and eliminate the issues related to the tooling is the use of toolingless additive 3D printed sand, which really opens up the whole freedom to the design engineers and the production engineers to really go after thin wall repeatedly. So in terms of the technologies, which I will cover, the new alloys or modified alloys with relevant properties in order to get the target goal of lightweighting, and then expand a little bit more on the additive 3D printed sand, compare it with the traditional sand casting, or maybe a combination of hybrid traditional sand mold with 3D additive core package. Plenty of opportunities there. In some alloys, thinner walls have better mechanical properties than thicker relatively. So this is kind of counterintuitive to the design engineers. The mechanical engineers, they tend to get a little nervous and say, hey, I want to add up the thickness based on what FEA told us, just to be sure. But in some cases, by adding thickness, you are deteriorating the properties. So thin walling actually does provide, because of higher cooling rate, better properties with some alloys. For example, aluminum 206, 356, the commercial alloys. Only the directionally solidified alloys, for example, steel, where drafting is useful to get a nice feeding channel established, but otherwise for most of the iron and short freezing range alloys, the tapering really is not required unless you are going with the conventional tooling that you need the taper to draw the tooling out of the sand. So this is out of our melt R25 that we developed to make thin wall ductile iron castings, high fluidity alloy that helped us fill successfully thin wall castings. And here is an example of experimental work that just simple spiral fluidity spiral, which is quite popular. Years of work has been done in this area just to measure the fluidity of and compare between alloy A and B type. So what we did is we kept in the simulation as well as in the experimental conditions all the process parameters, and such as pour temperature, time, the type of the mold material, the apply the vent and on. And we got a feel for this particular lift alloy that we got higher fluid distance. This is the one way we measure is the overall length or the maximum dimensions. Here we got like 21.5-inch versus 17-inch, the commercial alloy. And we were able to simulate, get a feel for before we actually ended up making the prototype castings and plate castings. So that was on spiral. Then we made finger castings. It's a typical 60-45-12, the commercial alloy, and these are the process conditions. And you can see, the filling pattern quite uniform. What you see here, so we had thicknesses from 2 millimeter, 2.5, 3, 3.5, 4, and 6 millimeter, all poured under the same tree. And we just wanted to see, this is quite common that any industrial casting, you may have a combination of all these thicknesses, and we want to make sure in the high stress area, it predicts the properties and the soundness that the mechanical engineer wanted to have from FEA and fatigue calculation. So one thing we learned from a lot of this experimental work with the support of university, Michigan Tech University helped us. They were part of the team on this. Is in order to make thin wall, you really need to have better temperature and process control because it's quite sensitive. Temperature of plus or minus 20 degree, what you see in the commercial environment may give you a totally different result, and you may not succeed. So you need to tighten up your process controls. So the point here is with the different section thickness, we obviously saw different certification rate, different cooling rate, different gradient. As you would expect, this is the thinnest and this is the thickest, and when we went down further into predicting the microstructure, this is where you see fraction of ferrite, which is strictly driven by, for the same chemistry, a cooling rate. So higher the cooling rate, you will have less ferrite and more perlite, and that would have an impact on your properties, the most important being the elongation. As you can see, it's the same casting, same chemistry, different wall thicknesses. And in the thinnest wall, we found, around 2% where we really wanted, 12%. So that led us to modify the alloy to get 12% elongation in the 2 millimeter wall thickness. And this kind of work helped us create the stage and set up the direction for the research in order to achieve that. So this again also lays out the importance of ICME tool as part of the new product development for thin wall castings. Again, modeling simulation is based on, the data, and you need to calibrate. So, when we poured these castings at a small foundry, part of our team, we instrumented with thermocouples, position at the known locations, and captured temperature time, recorded, and we got a good match. We thought we were pouring at 1300. Actually, by the time we got the metal into the sprue, we were around 1275, and that match fairly well with our simulated conditions. We put some thermocouple in the metal as well as in the mold. So that basically wraps up, making thin wall castings, the things to really look after, and how you may have to work on expanding your alloy scheme, make some modifications to get what you want. In our case, fluidity and better properties. Additive manufacturing, I'm sure most of you are quite familiar with. Our version of additive is strictly printing a mold without tooling, or printing a wax pattern without a wax die, for making investment casting, or printing a mold out of silica sand or zircon or chromite and make mold, and you just pour the metal, which is quite different than additive manufacturing as understood. Metal additive, where you build layer by layer using either metal powder and build the actual physical part. What we are doing here is we are actually making a cavity and pouring the same commercial alloy with the same ASTM spec, with the same known behavior, and only the magic is you don't use tooling. So that opens up a whole opportunities for design engineers to do, removing the draft or having a backdraft, put the fillets radii where you want, which you could not do because you are constrained by the parting and the tooling restrictions. Consolidate, some of the welded, bolted features, put them as part of your casting and come up with the one-piece casting design. And it's our experience, we do get much tighter dimensional tolerances. So that is the area I have an example that there is an opportunity for lightweighting without even doing anything, just by switching process from conventional sand casting to the 3D printed. You can really easily gain weight reductions, and then of course topology optimization. You can punch holes wherever you need in the low stress areas. You don't have to worry about adding a core or anything. It's a self code, and so it gives a tremendous freedom, and that helps us with going after more fabrication to casting conversions, make cast sub-assembly by eliminating welded, bolted, riveted joints into, and then even further combine functionality into one piece by looking at a sub-assembly and combining multiple operations into one piece of casting that will fulfill multiple functionality. And precision sand casting process, that is how we try to label this 3D printing process, so that there is a distinction compared to the conventional sand casting. It is a sand casting, but it has much higher precision and tighter dimensional tolerances. So that is another way we can do some lightening. So the simple trick is, if you just remove the draft, it's in our experience, we have done quite a few projects. You can see anywhere from 5 to 12% weight reduction. Now this is low-hanging fruit. We don't really have to do much engineering around it. One point I would like to make is, there are, as I said in the beginning, a lot of topology optimization.
Casting, all castings. Oh, lift is the lightweight in the future for tomorrow in Detroit. I mean, most of I know I kind of blow it out. I just register.
Hey guys.
Yeah, we're talking the same things we are working on. Yeah. Talking about.
Can you mute, please? Okay, thank you. So, topology optimization, it's the computer which does all the magic. It does help to see where you can take the weight out, but you need to have a traditional approach, based on manufacturability, like how the metal is going to flow into these thin areas and what kind of gating system, would even guarantee that you will be able to fill this part consistently. So I would say, use that as a tool to get some directions, but ultimately go with the traditional approach of design optimization, validate with virtual simulation for any thin wall casting development. So I have a couple of examples. This is actually a portion of a much larger casting that we helped an agricultural OEM. And this is the conventional sand casting. One of the issues they were having is, when they were milling this pocket, they really wanted to have a machine relief area, and in order to do that with the conventional casting, you would require a core the way it is parted, and we saw that as an opportunity. So we came up with, and this is how the whole Cast-Fab Sub-assembly looked like. So here is the casting, here is the welded plate with the braces, and here is FEA based predictive stresses. Here is the loading. There's a bearing which goes in, and so this is how it is made currently. And what we did is we went with the additive route using 3D printed sand and gain about 15% weight reduction, and reduce the stresses, maximum stresses from 72 KSI to 60 KSI. So there is a potential for further lightweighting, or because this is a highly fatigued, with lower stresses, you will see a longer life of these components. It's a high cycle fatigue. So this is the bracket design we came up with. Combined, stiffeners on both sides. They wanted a relief area. We were able to do that, and also this is from my experience making locomotive truck frame, where if you just have a regular hole, cord hole, you lose the material and the stiffness. You can regain some of that by putting a bead on both sides of the cord hole. And traditional castings means this will create a backdrop. Either you need a loose piece or you need additional cores, and that would impact consistency. So additive, the 3D printed sand really offers tremendous flexibility and a solution which improves the design. And we were able to incorporate machining relief area and drop the stresses from 72 KSI to 60 KSI. Another example is really I want to demonstrate what you can gain with tighter dimensional tolerances. And that's another quick low-hanging fruit. So we looked at a carbon steel cast valve body, WCB, 1000 PSI test, working pressure 500, minimum wall thickness 12 millimeter, which was derived based on the ASME code and FEA, and conventionally it's a split pattern with 2-degree radial draft on flanges, parting line gating, core box, core prints. Core print clearance is 1/16 of an inch per side, and we converted that. We looked at that, and so the point here is, if this is one of the standards being used in the industry for dimensional tolerances, ISO 8062. The conventional sand castings are typically in the range 10 to 14. This is, by the way, this table is a function of the processes and the dimensions, the basic dimensions. So if you look at here, conventional sand castings, let me get rid of this. It's anywhere from here to here. The investment casting would give you the tolerances spread 4 to 6. And based on our limited experience, what we see is the 3D printed sand kind of gives us pretty close to the investment casting. So say, for example, instead of picking C11, and if you pick C5, look at the variability on a key dimension. It's plus or minus 3 versus plus or minus 0.38. So simple stuff means your current casting wall, and this is the current design. I don't know if you can see it clearly, but the wall thickness is are given here, and with the tolerancing, you have to have whatever is the design wall, 12 millimeter plus at least 3, so 15 millimeter, whereas you can go 12.38 or 12.4, and you will still be okay with the minimum wall thickness requirement. And just by doing that simple trick, we validated to make sure the stresses don't go out of range. And this is the conventional, this is the volume. I have a summary which we will go through. Here is the core you need, and with the core print and the clearance. So with the 3D printed route, all the drafts are gone on the flanges. That helped us gain some weight, tighten up the tolerances, and we were able to, keeping the same stress level, we were able to reduce, and this is how the design looks with no draft. We also thought there is a possibility of making a self core, so you really don't have to have a core even with the 3D printed. And there are ways you can get the loose sand out by creating the pockets, unbonded sand. And we gained 15% weight reduction, 15% weight reduction here. And another thing we saw happening is it improved the quality with shrinkage predictions, and because of the cooling rates, this is with the conventional design. This is in the drag, which is very difficult to reach. You almost have to use a cast chill. Here, you have the shrinkage within the acceptable level, much reduced, and overall it's a win-win situation. We reduce the machining stock. So this is a good example to demonstrate simple things like tightening up the tolerances and removing the draft you can get, and this is without even making any changes to the alloy, 15% reduction. This is actually a quick repeat just to demonstrate the point that ICME is so valuable. And this is part of the MELT 51B project on thin wall aluminum that was spearheaded, managed by Boeing, where we were able to predict the porosities and the hot tears. We ran a bunch of casting. It's a 3 millimeter wall thickness. And we were able to find a very good correlation to what the X-ray results showed us. And so, you know, these predictive tools are quite matured. You just have to calibrate and use the right database, and you would get good results. And in fact, we have gone to a point where we are able to help clients in establishing acceptance criteria for like shrinkage and cracks, you know, based on fatigue and by estimating the critical flaw tolerance in casting process simulation. And then the last I would leave with, this is courtesy of Greg Peterson, LIFT, MMTC, MEP engineer, lead engineer, has been working on it. It's a C2 Corvette lightweight hybrid frame, which has shown tremendous value in reducing the weight of the order of 30 to 40%. And we are looking at some of the nodes to make out of 3D printed castings. There are 4 nodal castings, which you know, we have thoughts together for redesigning to get thin wall 3D printed. We are actually looking for an OEM partner for off-highway military type applications, or even a hybrid autonomous light rail applications, applying some of these composite and casting hybrid technology. So with that, quickly I will wrap up. You know, we are as a company, you know, we have worked with over 150, including Fortune 100 companies. They are maybe 20 times more or 100 times more capabilities than our size little company, but we come across as their extension of advanced engineering resource for especially dealing with casting, and that's our niche. So in a wrap up, I would say thin wall casting technology is a viable solution for lightweighting using current state-of-the-art technologies, which are mainly ICME or extensive simulation modeling, using the right database, opportunities of using new alloys or developing new alloys. And I would say, you know, if you want to do it in the current production environment, you would need better process controls. And it's always, you get fruitful results when you use knowledge and experience to come up with the manufacturable solutions. So with that, Joe, I think I'm wrapped up. If you have seen any questions, I'll be happy to tackle.
Thank you very much. As a reminder, if you do have a question, please use the chat function on the GoToMeeting taskbar, and you can address them again to the organizer, and those questions will come right to me. So thank you, Jiten, for that presentation. It's really good examples of how lightweighting isn't necessarily dependent on, you know, swapping out materials, but going to design and going to process, things like that can yield the lightweighting solutions people are looking for. Again, if people have questions directly you want to address Jiten, you see his contact information up on the screen. I'd encourage you to reach out to him directly with any questions going forward. And we have a couple of minutes left. So so please, if you have questions now, use the GoToMeeting taskbar. One of the questions that came in, Jiten, is what type of sensors are in the greatest need?
Yeah, that's a good question. Actually, we are involved with this is some preliminary work for using Wi-Fi technology and embedded sensors in the mold. And you can get not only thermal, but you can get vibration, acceleration, kind of data to validate and calibrate your simulation. So, typically in the foundry, we have quite sophisticated IR cameras, thermocouples, immersion pyrometer type for temperature measurements, which is very important, along with the whole slew of PLCs in the modern foundry you will see for capturing the mold hardness and moisture content and binder. And so, yeah, we as an industry are quite sophisticated, and especially with the big IoT, we are generating a lot of data. In fact, we have another project, DLA funded, that we are using a hybrid of meta modeling and simulation to get even further accuracy on predictions. So, good question.
Excellent. Thank you very much. We might have time for one more. I do want to be respectful of folks' times and make sure that we are wrapping up at the top of the hour. So again, any other questions? Please feel free to use the chat function there, or reach out directly to Jiten with the contact information you see on your screen. I don't know that we have any more questions for you, Jiten. So we certainly appreciate your presentation today. Appreciate your willingness to reach out to the folks that are online today. Hopefully they do reach out to you with questions, and we certainly, as always, appreciate your participation here at Lift. So please join us every third Thursday of the month for another Liftoff webinar series featuring some of our small and medium-sized manufacturing members. We look forward to their presentations each month, so stay tuned to your emails and stay tuned to the website, and we will be back with you next month. Again, thank you, Jiten, and thank you everyone for joining. We'll talk to you next month.
Thank you, Joe.